session, it will be the keynote session about architecting network for AI. So we will turn to a large-scale infrastructure and cloud. So at this time, I would like to invite Mr. Tyson Ramoros, Senior Vice President of Cloud AI from Arista, architecting network for AI. Please give him applause. Thank you.
Check. Hi, everybody. First off, thank Dr. Ack for inviting me. It's a pleasure to be here, and I'm going to talk a little bit around architecting networks for AI. So less glamorous than cybersecurity, less glamorous than model building and research, but critically important to the operability, reliability, performance of these systems. I'm going to touch a little bit on some level setting. We'll talk about problems that exist, solutions we're building to solve those at Arista, but also at large in the industry, and we'll look ahead a little bit to the future as well on where we think the networks are going, where the problems are going to exist, and the next set of solutions that need to be built for them. So let's level set quickly first. What is different about AI versus a traditional cloud or data center network? If you see the two graphs on here, the traffic patterns look very different. With AI, we are building supercomputers now. They're tightly coupled systems as opposed to the loosely coupled distributed systems that we've seen in microservices and service-based architectures over the last probably decade or two that have emerged. These highly coordinated systems rely on a small number of flows with a lot of data to move, as opposed to the statistical multiplexing benefits you get in a data center or cloud, where you have lots of diverse types of traffic, packet sizes, flow duration, but also intelligent architectures, recovery-oriented compute principles, reliability and availability models to be able to deal with failure, cope with failure, restart, and generally a little bit more of a loose requirement in terms of patience for the end customer or the end service that is performing a transaction on the network. So these tightly coupled systems in AI, because they're operating really in unison as one system, are very sensitive to problems that exist. That could be congestion or failure inside of the network. So this creates a new set of challenges that we have to solve for in our networks when we're building these AI supercomputers. So what does a supercomputer itself look like from a network perspective? We see four types of networks to comprise that supercomputer. There's the front-end network, which looks like a pretty traditional spine leaf model in this diagram. This is a pretty traditional network, to be frank. This connects to your storage, your services, your WAN, your internet, the rest of your compute services in your data center. So for all intents and purposes, you can think about that as kind of the data center or cloud-facing side of the network. There's the scale-out network, which is really where all of the GPUs or XPUs are interconnected for transmitting traffic via collectives, RDMA traffic very specifically. So this is where these new tightly coupled, highly constrained, highly orchestrated traffic patterns emerge. And then there's the scale-up network, which is an even more bandwidth-intensive domain. So these are direct connections between GPUs and XPUs. Typically, historically, they've been on a motherboard inside of a server. We're seeing that expand to rack scale now. And this is something that I think the industry is continuing to press on. How do you make these domains larger? But this is the most sensitive type of traffic, the most bandwidth. If you think about it, an XPU or a GPU can have hundreds of terabits per second of traffic memory bandwidth as they share memory as a single pool and operate really in unison as a single unit of capacity. Then there's the scale-across network, which is how you interconnect pods or clusters of GPUs or XPUs together to create an even larger supercomputer. So when you think about a supercomputer and AI networking, you're always really going to see these first two networks. Those have to be managed independently. The scale-up you may or may not see inside of that network, because if you have one GPU or one XPU, you don't need a scale-up network. If you're buying an architecture that has all of these embedded onto a single motherboard, that's provided to you native onside the board. So it's really when you start to talk about scales of hundreds or thousands of XPUs or GPUs that you start to see scale up. And then scale across is really reserved for multi-data center architecture or multi-data hall architecture. So those are really the tens of thousands, hundreds of thousands of GPUs or XPUs. So let's zoom in on scale out specifically. It is, as I said, the most intensive part of the network where all the RDMA traffic lives. We tend to see three architectures inside of a scale out network. There's a three-tier on the far right side, in the center a two-tier, and then on the left a single-tier network. So generally what's driving your choice here is the scale. There are trade-offs that exist across all of these, and inside of an organization when it's choosing to build, buy, operate a GPU cluster or an XPU cluster, they have to manage lots of other things. Organizational capabilities, the access to space, power, chiller plant and cooling capacity. Those might dictate choices in your end state of what you choose to design, how you architect. Maybe you deploy many parallel clusters, maybe you choose to do one super big cluster, but really these three architectural models are the ones that you're going to draw from to be able to do those deployments. And what's common across all three of them are the traffic management challenges or the congestion control within it. As I said, because these systems are highly coordinated and highly sensitive to fault and congestion, being able to get your traffic management right is really critical for managing your reliability and your performance. It's a very expensive infrastructure. You want it to come up, you want it to stay up, you want it to work continuously. If you're dealing with fault, if you're dealing with congestion inside of your network, you're creating slowdowns inside of that system or potentially even crashing jobs if you're running a training workload, which leaves a lot of idle capital, slows down your organizational capabilities. So it's really important to have sophisticated congestion control techniques. If you look at the bottom, you can see what is typically called classic equal cost multipathing approach, ECMP. This exists in most networks, most data center networks, cloud networks, and works well enough for most types of traffic. It's really terrible for AI, really terrible for supercomputing. So you can enhance that slightly by looking at a little bit more information inside of your traffic to be able to improve the amount of entropy you have and increase the efficiency of your load balancing. So this is RDMA-aware ECMP hashing here. There are other techniques to do this on a normal network as well, but this specifically is looking for information in the header related to the RDMA traffic itself. It's okay, I would say. Still, you're going to run into congestion events, and you're probably architecting your network then to cope with the type of congestion you're going to see by communicating things like pause frames using PFC or congestion notification, which again allows you to recover your network and restart your job, but is impacting ultimately the efficiency of your system. So what can be better than that? Dynamic load balancing. This is where your network is smart enough to observe across all of its paths, how each path is utilized, the flows that are transmitting across each of them, and then it uses a trigger to be able to determine if you're approaching a threshold that could be problematic and redirect some of that traffic onto another alternative path. Works a little bit better, still a reactive loop, and you're going to get some misbalancing, so you're not going to be as well utilized. Cluster load balancing is really a more state-of-the-art type of traffic balancing and congestion control mechanism. So we've pioneered cluster load balancing in Arista. Our systems support this. This is where you're looking at collective information in the traffic specifically, so you can build unique forwarding topologies in your network by being aware of the workloads that are running on your cluster. We've also pioneered another way of doing this. So instead of just saying, let's build a network of distributed system protocols and communication models and being able to manage the traffic as we're observing it, we realized there's a systems-based approach we could take here. So you see in our 7800 series devices, these are our biggest, most capable systems. We have a lossless, fully scheduled VOQ, virtual output queue-based mechanism for being able to distribute traffic across the system. So traffic comes in as Ethernet or IP. It is broken down into cells. That traffic is distributed in a lossless fashion across the backplane, reassembled on the other side, and transmitted out. We realized we could actually scale this out to a fully distributed system. So rather than saying it's just one system, let's have one control plane, but several systems that can run this same lossless fabric and really ease the burden on an end consumer or customer and being able to run their supercomputer without having to worry about all these congestion control mechanisms, fault recovery methods, endpoint scheduling techniques. Let's make it simpler for customers. Let's let the network do its job. And this has the added benefit, if we go back to kind of the single hop network, this typically have a limited scalability of 500 to 1,000 hosts or GPUs that you can connect to the network. This scales to tens of thousands of GPUs. So a very nice sweet spot of simplicity with the reliability performance that you require and scale. So beyond traffic management, another thing that you're solving for inside of these network architectures is really optimizing your TCO. The XPUs, the GPUs are a very expensive component. Power can be very expensive, cooling is expensive, there's long lead times, it's complex to build these systems. So you really want systems that are going to be cost optimized. It's very easy to, for any IT manager or executive leader to look at their network spend and say, that's the place we need to go squeeze. And so at Arista and generally in the industry at large, there's a lot of innovation happening inside of our network architectures, inside of our systems at the protocol level to improve TCO. So 5 really kind of key levers here that we tend to look at to drive optimization. The first is rapid productization and productionization of the latest generation switching silicon. So the moment it becomes available, you want to get it out to your customers as quickly as you can. This is very similar to the GPU and XPU cycle as well. We're constantly improving on our silicon, on our system, and as NVIDIA released, the Blackwell family, Hopper became old news very quickly. The same thing happens in switching silicon. We're all in on liquid cooling as well. So a single chilling plant inside of the data center to drive maximum efficiency. So not just at the infrastructure level for your cooling plant, but inside of all of your systems. You're going to drive much more efficiency here. You're going to be able to run your systems hotter, higher utilization, have higher reliability. This improves your TCO. Connections and connectivity and interconnect is super important as well. So third is really, you talk about it here in terms of optics technology. There's innovation happening at the cabling level electrically as well, but these clusters are very large, and so they're largely reliant on fiber optic communication. So we're driving a lot of focus in the industry around improving our fiber optic communications, lowering the cost, improving the bit per joule and efficiency of these systems. So it reduces power, unit cost, and improves your overall reliability in some cases. We're increasing AI switch rack density as well. So how much can you cram into a smaller space so that if you're space constrained, you can manage that? How many more connections can you build on a faceplate of a switch or a router so that you can build a denser fabric? Again, the smaller you make things, the more you can use electrical communications and fewer fiber optics. That improves your reliability and improves your cost structure. And then optimizing Ethernet fabrics for AI centers specifically. The example I showed on the 7700 is a good way to do that at the systems level. I'll talk a little bit more about how you do that more broadly at protocol level and across different types of systems in a minute. But let's go back to optics and interconnect. Historically, switch costs, router costs have dominated your networking costs inside of a data center. Because of the size of these clusters, because of the bit rate of the interfaces that you're using here, that balance is really shifted. Optics now dominate your cost, dominate your power consumption inside of your network in your AI center. Left to their own devices and let the industry continue to scale as it has, the problem only gets much, much worse. And so you can see in this example, 8,000 GPUs, XPUs, the cost is almost 85% concentrated into the optics themselves, and 60% of the power goes to the optics. So we've got to fix this. So how do you do it? Well, one of the things we've done at Arista is we've led the charge on what's called linear drive pluggable optics. So this is a traditional optical transceiver that plugs directly into your switches and routers. But what we've done is we've leveraged the capabilities of the latest generation switching silicon to allow us to remove the digital signal processing unit that typically was co-resident on these transceivers. That is the most power-hungry component of a transceiver. Historically, it's been needed to clean up the signal in your communication so that you have good signal integrity across your optical channel, but it's not necessary anymore. So we pull it out, we immediately save power, and in the process, we also improve reliability because we've removed a component that can fail inside of that link. This reduces your cost by about 30%. It improves your reliability by about 50% by getting rid of that component. It is the thing that fails the most often. Frees up more resources for compute. It lowers the latency inside these switch transceivers as well, which is an added benefit. So this is all done without making any compromises. There's nothing special, proprietary about this. It's simply taking advantage of technology evolution, productionizing it, and putting it and packaging it into a product. We've led the charge to go put together an MSA, so we build industry-based standards around this, which we at Arista think is very important. It's important to have an ecosystem of contributors, innovators. It's important to have interoperability. So standards are super important to us, and we've done that with LPO, but we're leading the charge here. We have more LPO-type optics available at more speeds across more devices than anyone out there, but we're welcoming the industry to obviously catch up, and we're going to continue down this path as well. So when we talk about standards, it's not just in the hardware as well. Ethernet is also very important to us at Arista. We're big believers in it. All of our devices are Ethernet. And one of the reasons we believe in Ethernet is because of the benefits of those open ecosystems and standards. So you've got interoperability, you've got economies of scale, you've got an industry at large that adopts. This is a technology that people are familiar with. They know how to operate, so you don't have a gap in terms of knowledge or capabilities in industry. And we've been seeing Ethernet gain momentum inside of these large AI centers and GPU, XPU clusters for some time. If you look at the top 3 charts over the course of about 12 months, a little less than 12 months, one of the analysts that is pretty deep in the networking space, Deloro, revised their forecast from saying Ethernet would switch over and overtake InfiniBand as the leading technology for back-end scale-out fabrics from 2028 to saying, actually, it's happening right now. So in less than a 12-month period of time, they pulled in by 3 years their forecast. Another analyst, 650 Group, who closely tracks supply chain shipments, validated that. They said that it's not just about money. It's not about POs being cut. It's not about where customers are spending their money. It's actually in rate of deployment when we see ports being spent. And during their last earnings call, NVIDIA even said, hey, listen, we have IB, we have Ethernet, but we're now seeing attach rates on Ethernet roughly equivalent to our historical shipment volumes on IB. So this switchover is happening today. Ethernet's gaining its momentum. Again, the power of standards, super important here. But it's good enough and it can be better. So there's a couple reasons we also see people switching over to Ethernet. It's because the innovation is happening to improve the protocol stack itself. So the Ultra Ethernet Consortium was founded to be able to go drive improvements to Ethernet specifically for GPU, XPU clusters and AI supercomputers. Ethernet works well, it's reliable, it transmits bandwidth great, high bandwidth, but we can actually make it better by improving the ability to spray traffic, the congestion control problem that I talked about earlier, ramp up connection time faster, have better independence on packet ordering so things can come in sequence, out of sequence, we can reassemble them without impacting performance. We can embed security, so we have better cryptography and security control over this traffic from day one. And better link end-to-end congestion control so that we are rapidly responding before a problem occurs inside of the network. So we have Ultra Ethernet support in all of our systems today. There are several providers that are out there. This is really dependent on the endpoint, though, so you need a network interface card to be able to support Ultra Ethernet. There are some shipping at 400 today. The 400 gig varieties have been shipping for about a year. The 800 gig are coming in the next 12 months. So we see this is going to continue to drive a lot of that momentum on Ethernet. And there's another place that Ethernet is being applied, which is back to that scale-up network. So if this transport can work so well across communicating on the scale-out network, we already use it on the front-end network, why not apply it to the scale-up problem as well? So Ethernet for Scale-Up Networking, or ESUN, was announced at OCP, the Open Compute Platform, in September last year, or just actually this year, so we're not in 2026 yet. And it's doing many similar things to what Ultra Ethernet is doing. The whole idea here is better header efficiency, a better link layer, faster recovery, lossless capabilities. This is really about dedicating as much of the pipe to data as you possibly can, getting all the overhead out of the protocol itself, and then making it work reliably in a fashion that allows you to scale that up at low cost with high reliability and with the performance that you need. I'd be remiss if I didn't talk about the need of software and management inside of an AI supercomputer as well. So another key point to your network architecture is being very thoughtful about how do you manage this network. Automation is key. At Arista, we have a bunch of investment happening in agentic AI actually to help with that solution. Change controls, governance inside of your corporate infrastructure is super important, but very important is observability. Very important is the ability to secure and segment traffic so that you can actually know that you're able to serve the disparate needs of your business, your organization. And then the operational certainty that when devices fail, you know exactly why they failed, when they failed, and how you can recover from them. A lot of people overlook this aspect, the network management system aspect of building these AI supercomputers. They focus on the systems, the technology, the cost, they get to the deployment, and then they end up stranding their capacity for months as they try to stabilize the network, as they try to stabilize their AI supercomputer to get it up and running and working. And then once it's functioning, managing those failures. So again, you're wasting a lot of money as an organization if you spent a considerable amount of time, energy, effort on building and investing into this AI supercomputer, and it's sitting idle. So the software ecosystem is really important here. One of the things we've done and recognized inside of Arista is we've poured a lot of energy and effort to enhancing our existing system called CloudVision into scaling to meet the needs of the supercomputer. But again, putting some more sophistication in here as well to look at the end-to-end performance of the workload. We've built an AI agent that runs resident on the host so that it integrates into the fabric and looks at the network traffic holistically, can help you with understanding what jobs are running where and how it correlates to the traffic inside of the network. So that this eyes, ears, and hands, if you will, of the network, the digital version of those, is really essential. And if we look ahead, where are we going to see the network technology continue to drive forward? I put a few things in here. I mean, this is a non-exhaustive list. There's so many other innovations to happen here. I probably missed something incredibly important that I just oversight and didn't get it in here as well. So forgive me if you've got a lens on something you think is critical here that I haven't actually mentioned. But optics and cabling innovation. So I talked about that interconnect and how important it is. Better reliability, lower cost per joule, more density. So there's a lot of interesting things happening here to get out of traditional optical transceivers. So one methodology that is gaining traction right now is called slow and wide. Historically, we've been looking at networks over the last probably couple decades as speeds and feeds need to keep increasing. That single lane speed has to go up, and I need more ports of it. And so I just have to make everything bigger. The answer in AI supercomputers isn't necessarily just make them bigger. It's actually, well, you know what? There's some very efficient ways of communicating at lower data rates and parallelizing those paths, coupled with the systems designs, the protocols, and the methodologies that we're building to manage traffic inside of these networks so that you can use these technologies to operate them and actually achieve your goals. So we're doing things at the physical level with XPO and how you package these together, NPO on board and CPO, so co-packaged, near-packaged optics, so you put them in and integrate them into the system. We're driving innovation in also the connectivity model of physical connection, so really L1, EBO, expanded beam optics is really important, we think, to be able to increase the reliability of your fiber plant. So this it's much less sensitive to dust and debris. You can connect it, it comes up, it works right. For anyone who's actually spent any time building and operating networks inside of a data center with fiber optics, they know how painful it is to deal with dirty fiber, how often those create issues for you. So this is really important. Hollow core eliminates the center of the core of the fiber itself, reducing latency, so you're transmitting the laser through vacuum as opposed to through a physical medium. And so there's just going to continue to be a ton of innovation happening here. Deeply integrated mechanical designs is another one. We're seeing a lot of this rack scale solution coming together. So this is where the whole system is thought of as a singular unit as opposed to disparate components that get assembled. These mechanical designs involve everything from chiller plant to management systems to the switching to the compute itself. So this is really about managing and speeding the supply chain and managing the deployment and turn-up speed of your network and your cluster once it lands into your data center. More cooling innovation. We're seeing things like two-phase inside of the liquid cool plant. So this is a way of building a closed-loop system and being efficient with water and being able to use things to do direct liquid cooling to your compute, but with a very efficient thermal medium rather than just chilled water, and you don't have to evaporate anything. There's immersion cooling that has happened where you're actually sinking things directly into either types of mineral oil or in some cases PFAS type materials to be able to cool them. You actually boil the liquid and evaporate it and then recondense it and create a closed two-phase loop to be able to drive maximum performance and efficiency. And then I talked about slow and wide versus fast and narrow as well. So we're going to continue to see a lot of push here, especially as the electrical signal integrity problems become more significant at the current speeds that we're seeing with like 200 gig and 400 gig lanes. So in summary, like the architecture is multifaceted. We talked about systems, we talked about topology, traffic management, we talked about innovation that needs to happen on underlying technologies, protocols, and software. It's really a closed loop when you're talking about looking at your network architecture. It's not just about minimizing the cost or maximizing reliability. You've got to have purpose-built fabrics, and so you're being very intentional about what, why, how you're building your topology and the choices you're making. Optimizing for application performance through your management layer and your protocol choices. Optimizing these fabrics based on your choices for interconnect, for scale out, scale up, and scale across. Increasing switch customization, and that extends all the way to these mechanical designs and cooling designs. And then the physical layers, the connections, the density that you need to have. All of these things are happening in parallel, and I think this nice ring diagram just shows how much of a closed loop we have. We've kind of gone from the world in cloud of loosely coupled, as I said, distributed systems, to coming back to the notion of these very demanding, tightly coupled, singly orchestrated systems. It requires a holistic approach to building and architecting the right network. And that's it. Thank you very much.
Thank you, sir.
Thank you. Thank you very much for the keynote session of Architecting Networks for AI. Thank you, Mr. Tyson Ramoro, Senior Vice President, Cloud AI from Arista.